You can buy a hand-built all-metal airplane, engineered before color television, for less than a new dishwasher. While cars rust and plastics crumble, these polished relics endure, functionally immortal, thanks to forgotten engineering standards. The world insists that nothing lasts, yet these planes won't die. So why did an era obsessed with progress quietly master permanence? The answer, hidden inside the honest aluminum still gleaming on American runways, is stranger and more urgent than you have ever been told. Aluminum changed everything. Before the 1930s, small planes were built like old barns, steel tubes wrapped in fabric, stitched and doped, every surface a patchwork. Then, the first time an engineer pressed a thin sheet of aluminum over a curved form and riveted it to itself, a new idea took hold. Let the skin do the work. This was monocoque, the eggshell principle. Instead of a skeleton hidden beneath, the metal skin itself became the structure. Stress flowed across the surface, not down a spine. Imagine squeezing an egg in your fist. The shell, though paper-thin, spreads the load in every direction. It is the same with an aluminum fuselage. Load paths run from nose to tail, wingtip to wingtip, each force diffused by the curve of the skin and the lines of rivets. The Luscombe 8A and Cessna 120 were among the first American light planes to trust their lives to this principle. Their designers used 2024 T3 aluminum, often with an alclad coating, a pure aluminum layer fused on both sides to resist corrosion. This was not just about strength. Fabric rots, but alclad forms its own oxide shield. Maintenance became a matter of wiping down metal, not patching holes or testing for hidden rot. The monocoque fuselage meant fewer places for water to hide, fewer seams to fail. Riveted joints, when kept clean and tight, could last for decades. Pilots and mechanics began to trust the shine of bare aluminum. They knew that as long as the skin was intact, the airplane was strong. They polished, not painted, letting every reflection reveal the health of the structure beneath. Even today, a 60-year-old Cessna can stand outside in the rain, its strength visible in every curve and seam. The monocoque revolution was not just a technical leap, it was a cultural one, the moment when honest metal replaced the hidden fragility of fabric. The age of the eggshell had arrived, and with it, a new kind of permanence in American aviation. A polished aluminum fuselage tells its story out in the open. Every streak, every fingerprint, every patch of dullness is a message from the elements or from the hands that care for it. For the owner of a Luscombe or a Cessna 120, maintenance becomes a ritual. Walk the line, run a hand along the rivets, squint at the seams, listen for the soft rasp of oxidation. Corrosion on alclad aluminum shows up as a faint white blush, easy to spot and easier still to polish away if it is caught early. Compare that to the old world of fabric and dope. There, decay hides in silence. A mechanic tests for rot with a punch, pressing a thumb or a blunt tool into the fabric, hoping not to find a soft spot. Sunlight is relentless. Ultraviolet rays break down the dope, turn linen brittle, and open the way for moisture to creep in. A single season outside can doom a fabric wing, while a metal one shrugs off rain and sun with a wipe and a coat of wax. The pride of a polished airplane runs deeper than vanity. It is a practical ethic, labor spent on the surface that pays back in decades of service. Owners gather on Saturdays with rags and polish, not to chase perfection, but to keep the structure honest. Every swirl of polish is a check for corrosion. Every bead of sweat is a small investment in another year of flight. Unlike fabric where rot can eat away unseen, aluminum makes its wounds visible. A restorer can spot a problem before it becomes a threat. This culture of stewardship is not about luxury, but about vigilance and respect. The effort is measured not in dollars, but in hours spent and hands stained black by aluminum oxide. A 60-year-old Cessna left tied down in the rain can still gleam, its strength obvious to anyone who cares to look. The metal invites inspection, it rewards attention, and it forgives neglect only so far as the owner is willing to work. That is the deal. Honest labor for honest aluminum. This is how a machine becomes more than a tool, how it earns its place as a survivor in a disposable age. Student pilots are the ultimate test pilots, at least for landing gear. Every flight school veteran remembers the sound. A Cessna 150 slamming onto the runway, the gear flexing, the airframe shuddering, and then, sometimes, a bounce that sends the whole airplane skyward again. The secret is in the metal beneath the floorboards. The Cessna's main gear is a single leaf of spring steel, cold-formed and bolted to the fuselage. When a student drops the airplane from a few feet up, the steel leg bends, storing the impact as elastic energy, then snaps back, launching the airplane upward if the pilot is not quick with the controls. There are no seals, no fluid, no moving parts, just tempered steel doing its job. The simplicity is brutal, nothing to service, nothing to leak, and almost nothing to break unless you bend it past the point of no return. Piper's answer was different. The Cherokee 140 rides on oleo struts, essentially a hydraulic piston surrounded by compressed air and oil. On touchdown, the piston slides into the cylinder, squeezing oil through a tiny orifice. The air acts as a spring, but the oil turns the vertical motion into heat, bleeding off the energy in a single, deadened stroke. The result is less bounce, more control, and a landing that feels like dropping onto a cushion instead of a trampoline. But the trade-off is complexity. Oleo struts need regular attention, fluid levels, nitrogen pressure, and fresh seals. Ignore the maintenance, and the strut goes soft, bottoms out, or starts leaking, leaving the airplane riding low and vulnerable. In physics terms, the Cessna's gear is a spring. The Piper's is a spring and a shock absorber. One stores energy and gives it back, sometimes too eagerly. The other spends that energy as heat, smoothing out the punishment. Both had to pass the same FAA drop tests, absorbing the force of a hard landing at 3 or 4 times their own weight. But for the instructor in the right seat, the difference is visceral. The Cessna trains you to respect the bounce. The Piper forgives you once. And in the world of training aircraft, that choice between simplicity and sophistication is more than a matter of taste. It is a bet on what will survive decades of student abuse. A mechanic's hands tell the story of the Continental O200 better than any brochure. This engine, bolted to the nose of a Cessna 150, looks almost primitive by modern standards: air-cooled, 4-cylinder, carbureted, and stubbornly simple. But its real secret is not what it has, it is what it does not need. The O200 runs a compression ratio of 6.75 to 1, far lower than the high-strung engines found in most cars. That means less heat, less pressure, and far less stress on every moving part. At full throttle, the red line is 2,700 revolutions per minute, not much faster than a riding mower. This is deliberate. Lower revolutions per minute mean the pistons travel fewer miles for every hour flown, and the bearings, valves, and crankshaft all live easier lives. Inside, the tolerances are forgiving. Rings can wear, valves can get a little leaky, and the O200 will keep running. It is a tractor engine at heart, designed to run on low-octane fuel and shrug off neglect that would sideline anything more exotic. Mechanics call it honest because it never tries to hide what is wrong. If it is tired, it burns a little oil. If it is neglected, it runs rough, but it rarely quits outright. The published time between overhauls is 2,000 hours, but many examples double that with careful maintenance and a steady hand. Oil changes, spark plugs, and valve adjustments are all within reach for an owner willing to learn. This philosophy matches the airframe it powers. The O200 is not built for speed or showmanship. It is built to keep flying, year after year, through the hands of student pilots and weekend mechanics alike. Where the aluminum shell resists rot and corrosion, the engine resists obsolescence by being easy to understand and hard to break. Together, they form a system with no single weak link, a machine that survives not through luck, but by design. In a world of throwaway machines, the O200 stands as proof that longevity is a choice, not an accident. Inside the Beechcraft Musketeer's wing, strength comes from a structure that looks more like architecture than aviation. Instead of ordinary ribs and spars, Beech built a sandwich of thin sheets of aluminum bonded to a honeycomb core. Each cell of that honeycomb is a tiny hexagon pressed from aluminum foil, stacked edge to edge, and glued between the skins. The result is a panel that resists bending and twisting far more than its weight would suggest. When a load presses on the wing, whether from turbulence, a hard landing, or the steady lift of flight, the force spreads across thousands of cells, each one sharing a fraction of the burden. This is the principle of the sandwich panel. The skins carry tension and compression, while the honeycomb keeps them apart, just as a steel beam uses flanges and a web. The Musketeer's bonded panels mean fewer rivet holes, fewer stress points, and a smoother transfer of forces from skin to spar. In practice, this makes the wing heavy for its size, but nearly immune to local dents and fatigue cracks. Owners who have cut into these wings for repair often find the honeycomb core intact after decades, the adhesive still holding tight, the aluminum barely marked by time. It is a kind of overkill, extra weight traded for a vault-like solidity. The price is paid at the fuel pump, but the reward is a wing that shrugs off abuse and keeps its shape long after lighter, more efficient designs have started to show their age. In the Musketeer, the honeycomb is not just a material choice, it is a statement about what matters most: lasting strength, not fleeting speed. Grumman's AA-1 Yankee came from a different school of over-engineering, a place where the rivet gun was almost an afterthought. Instead of fastening every seam with metal pins, Grumman's engineers turned to industrial adhesives and a bonded box spar. The main wing structure was built as a closed aluminum box, its skins, spar caps, and ribs glued together with structural epoxy in a factory jig. This was not a shortcut. A bonded joint spreads loads across a wide area, so stress does not gather at a single hole or crack. The result is a wing that acts like a torque tube, resisting both bending and twisting with a stiffness that feels almost uncanny in turbulence. A cross-section of the AA-1 spar on a workbench looks more like something from a bridge than from a light plane. No rows of rivets, no jungle of angles, just clean, uninterrupted metal, the adhesive line barely visible. The benefit is clear: fewer stress risers, fewer places for cracks to begin. The adhesive itself, cured under heat and pressure, forms a bond that resists vibration, flexing, and even the slow creep of time better than most expect. But this strength comes with a price. The AA-1 structure is heavy for its size, and the market never forgave its thirst for fuel. Owners today can find an AA-1 for under $30,000, not because it is fragile, but because it is built to a standard that outlasted its era. The hulls refuse to die, shrugging off decades of use, while their reputation for durability quietly grows. In the world of honest aluminum, sometimes the best insurance is a wing that was glued together by people who did not believe in shortcuts. An older pilot eases the throttle forward, sunlight glinting off the coupe's polished nose. Here, simplicity is not just a virtue, it is the whole design philosophy. The coupe's cockpit offers something almost unheard of in aviation: no rudder pedals cluttering the floor. Instead, a single control wheel governs both ailerons and rudder, linked through a system patented in 1937. Turn the wheel, and the airplane banks and yaws together, automatically coordinated. The nose wheel, too, is part of this mechanical handshake. Steering on the ground flows seamlessly into steering in the air. For pilots, especially those with less flexible knees or less time for training, this meant fewer mistakes and a gentler learning curve. But the coupe's minimalism goes deeper than the controls. Its trailing link landing gear soaks up rough landings with a forgiving motion, sparing both the airframe and the pilot's back. Hard touchdowns that would rattle teeth in other planes are shrugged off with a soft trailing bounce. The design was not just about comfort, it was about reducing the number of parts that could break and making every landing a little less dramatic. This approach, removing complexity instead of just adding strength, let the coupe survive in service for decades. Owners praise how little there is to go wrong. Fewer linkages, fewer adjustments, fewer surprises. In a world obsessed with features, the Air Coupe stands as proof that sometimes the smartest engineering is what you leave out. A Piper Colt sits on the ramp, its cockpit stripped to essentials, a pair of seats, a yoke, a throttle, and not much else. Produced from 1961 to 1964, the Colt was Piper's answer to the demand for a truly basic trainer. Unlike its sibling, the Tri-Pacer, the Colt left out the rear seats and flaps, reducing both weight and complexity. There is no hydraulic system for flaps to leak, no extra cables or pulleys to adjust, and fewer electrical circuits to chase when something stops working. Even the panel is a study in restraint, just enough gauges for safe flight, nothing to distract from the business of learning to fly. With only 2 seats, the Colt forced a focus on essentials, pilot, instructor, and the air beneath the wings. Every system removed was one less thing to break, one less repair to log. Maintenance becomes straightforward, fewer linkages to inspect, fewer hoses to replace, and a smaller chance that a hidden fault will ground the airplane. Owners praise the Colt for its honesty. If something goes wrong, it is easy to find and fix. This is subtraction engineering at its most practical. The Colt's simplicity is not about nostalgia, it is about reliability. In a world where every new model seems to add features and failure points, the Colt stands apart. It survives by having less to go wrong, and in the hands of careful stewards, that is often the surest path to longevity. Every year, nearly 80% of single-engine planes passing FAA inspections were built before 1980. These are machines outlasting generations of owners. As modern design trends chase efficiency over endurance, these aircraft stand as proof that durability is a choice, not an accident. The real legacy is not aluminum or engines, it is the standard we choose to demand. What survives tomorrow depends on what we value today. Share your thoughts below.